Afternoon, everybody. We shall continue our discussion on source coding. So today we shall discussion on source coding. So there are numerous kind of source coding people have used, and only two of them we have discussed here, and one or two we shall discuss whether uh, not based on probability distribution. So yesterday we were discussed arithmetic coding. I have made some corrections in the notes. So basically, uh, yeah. So this is the correction that we had here four messages: A1, A2, A3, A4. So therefore, there would be four stages: stage 1, stage 2, stage 3, stage 4. So this is not necessary. This was necessary for a message A1, A2, A3, A3, A4. It is there in the book, but by mistake I have put that stage here. And also because there are four stages, the choice of the number will come from the final stage, that is the fourth stage, and between this A3 and A4, that is between 0.068 and 0.072. So that can be chosen at 0.07. So now 0 in between this 0.07 could be the number, because there are four messages. And so next in the decoding we have to search for 0.07. So in the stage 1, 0.07 is here. So that means the first symbol is A1. Stage 2, the 0.07 is in the interval of A2. So second symbol is A2. Third symbol is A3 because 0.07 is falling in this interval. And the fourth symbol is A4 since 0.07 falls in this interval.
Sir, but we had to divide it two times, right? We were told last class if the width is double.
Yeah, so that is not necessary. Two times is necessary, was necessary for if the symbol, if the message is A1, A2, A3, A3, A4, then two times necessary. Otherwise, this stage 5 is not necessary. For four symbol, four stages are sufficient. Okay.
So, but
So
the receiver does not know, right, how many times each symbol is repeated in the message.
yeah, that's why this is not necessary. So receiver does not know, but receiver will basically see that 0.07 number, and then we have to see the number of messages. We have to send the number of messages. Okay. Otherwise, the full table need to be transported. So that is not desirable. So therefore, the receiver has to, the number of symbol need to be transported, and then we can have the symbols one by one coded. Okay. So that this can be, I have given two more examples. Okay, one with the same probability uh, table or the interval table we can say, because for arithmetic coding by definition depends not on specifically probability, though probability can be one of the means to create interval, but it will work for any interval. Okay. It's if once we define the interval and proceed partitioning the interval according to the message, then it is sufficient that it will be coded properly. So like here message is A2, A2, A1. Okay, we have this same probability table, A1, A2 interval table, A1, A2, A3, A4. So because the first symbol is A2, the interval A2 is expanded. Okay. So 0.2, 0.4, and in the same ratio it is expanded. So 0.2, 0.24, 0.28, 0.36, 0.2, 0.4. Again, we have A2, so A2 is expanded. So then this becomes 0.24 to 0.28, and subsequently these are the numbers 0.27 to 0.256. Now, because the last symbol is A1, so therefore the interval from where the value will be picked is this A1 interval. Okay, so A1 interval gives the value. So that means 0.24 to 0.248. This is the A1 interval in the stage 3. So from there, any value we can pick. So we suppose we pick 0.245. So, and in the decoder, 0.245 is here A2, and 0.245 is here A2, 0.245 is here A1. So that way A2, A2, A1 can be deciphered. The same message, suppose we take a different equal interval table. Okay, so 0, 0.25, 0.5, 0.75, 1. So again, here we are expanding 0.25 to 0.5 interval. Okay. Then next again A2, that is 0.3125 to 0.375 interval, and we give all these numbers. Okay. So finally, we have the last message, last symbol A1. So we pick this interval just like before, 0.3125, the between, there will be a point here.
So which stage we, like which interval we expand depends on the next symbol, right? Not on the how many times it occurs or something.
Yeah, yes. It is on the next symbol. So it is based on A1. So 0.328125. So we choose a good number. Again, in arithmetic coding, choosing this number is tricky because the binary train that we need to transmit, again, we need to convert this number, 0.32. Okay. So that need to be, in many cases, because of your wrong choice or some choice, it may happen that we will have a large binary string. So that is one of the disadvantages of arithmetic coding when we transport it in through binary system. If we have a decimal transportation system that is ternary system instead of binary, so then of course this problem would not occur.
So can we always pick a number in that interval which is possible to be represented in binary exactly?
No, because our communication is nowadays all technologies in transmitting binary data. So that way there are some communication in 4RE, 8RE communication is there, but those are rare. We shall discuss maybe one or two such cases later when we at the last about some 8RE or some other communication protocol. So there are many other source codings. Schemes, notable of them based on probability distribution. Also, there are many other. So notable of them is Gullam, I think. Gullam rice, which is often used nowadays. So that is again based on probability distributions. but there are some concept is little bit different. We will not go through it, but just to say this is one of the famous coding schemes that was introduced by Jean Ghulam in late 60s, early 70s, and then it was further enhanced by Rice. So that way Ghulam Rice coding is one of the famous coding scheme. Now we shall discuss little bit of some one or two coding schemes which are simpler in concept. Those are not that much based on probability distribution, so thereby implementation is simple because we do not have to compute the probability table. So run length coding. So this is a very simple coding. Usually run length means we take a symbol and then the number of times the symbol is continuously repeated is coded. So here run means the number of times a symbol is repeated. So thereafter, the symbol along with its run, that is the number of times it is repeated. So both are stored. However, generally this is efficient when we have a binary stream. Generally, it is used for binary data stream, where the probability of 0 and 1 occurrence consecutively is much more compared to, say, other kind of symbols. So it is used for binary data streams or binary maps. So this run can be this run and the run can be defined row-wise, column-wise, or zigzag in case of 2D maps, 2D binary maps. So basically, it is a popular method for a secondary coding for images. So by secondary, I mean that the primary coding could be either say Huffman or any other, or maybe even a lossy coding. Generally, for images, the primary coding scheme is a lossy coding. Followed by, which is followed by we will not go through the lossy coding schemes. Though I think one of the important type of coding schemes for source symbols are the lossy coding schemes. So because that will take again a lot of time, so we will not go through this. Once the run is computed, the code is represented by either say the symbol A, comma the length A0, L0, A1, L1, like that, etc. Or a stream of numbers usually starting from the number of ones. So that is L0, L1, like this. So here it is important that if we represent just the run by the run, not the numbers, it is possible for binary, okay, easily, because there are only two states in binary, 0 and 1. And if we in our protocol, if we embed that, we will always start counting the number of ones. So that means first number L0 is the number of 1. Then subsequently this will be the number of 0. So like that. So if we do like that, then it is possible that the string can be represented by a number. So let us take one example. Again, example.
Sir, that 2D binary maps, is it like a matrix comprising of only 0 and 1?
Yes, just that one I am giving. Example of a 2D map.
So the matrix is not of zeros and ones, right? Each entry in the matrix is a binary number, right?
Yeah. Matrix is not 0 and 1. The elements are either 0 and 1. So like this is a 2D map. Let us take a simple example. So now this can be scanned either row-wise or column-wise. So row-wise scan will produce the first is 0. So then either it will be represented by 0, that is the symbol, and the numbers, that is 6. Then next row, that is 1, 6, 1, 6, 2 row over, 1, 5, 0, 1, 0, 1, 1, sorry, 1, 3, 0, 2, 0, 6. So there are 4, 4, 8, 9 entries here. Similarly, column-wise also we can do. So row-wise scan means first row we will do, then only we will go to second row. Okay. But suppose for the zigzag scan,
So here number of rows has to be also informed, right? Like
no,
one per row.
number of rows need to be need not be
Number of
informed.
columns. Like in one row, how many columns? That has to be given otherwise.
Okay, okay. You mean to say the dimension of the 2D map? Yeah, dimension of the 2D map need to be given. Okay. But what is transmitted, that one object is transmitted having generally its dimension will be given and bitmap will be given. So that is like here it will be given that binary, so 2, okay. And then this will be table will be given. So those are generally given in the header file, a header, and you have to read the header and then this will go. And in the header it will be written that whether it is what kind of coding and all those things are given and how these are represented either in a ASCII code or a binary code. So that all need to be written initially, and then usually such kind of streams are given. So in case of zigzag, what will happen in case of zigzag? It will go like this and come like this. This is zigzag. This is the zigzag scan, of course, followed in this particular, coding, that is run length coding. There are other kind of zigzag scans are there, like this way also we have zigzag scan is available. Like this will go here, then it goes here like this. It will go That is also another kind of zigzag scan. But for run length, usually this kind of zigzag scans is there.
That
So
was
zero.
diagonal, right? The other one.
The other one would be like first it will go here and then here, then there, then from this side, and then like this, like this, like this, and this.
Yeah, diagonally.
Yeah, so that means one corner will be basically scanned. It will be scanned from the corner side. That is usually followed for some other coding scan. That is in JPEG, it is followed like that. So, but we will not discuss that. So, 1, 2, 3, 4, 5, 6, 12, 17. So 117 once, then 0, 2, 0. Zero 8. Now to transmit this scans, usually we can start with, say, as our convention that starting one would be run would be the run of 1. So therefore, in this case, say it starts with 0. Okay.
Sir, you wrote 1,17, but there is a 0 in between.
Oh, 0 in between. This is 6, 12. Oh, 0 in between. Sorry. Then we have 1, 0. Then we have 5 ones. 1, 5. Then 1, 0. And 1, 3. I hope it is correct now. So now the stacked runs can be transmitted.
So that is 0 2 times, then 1 3.
0, 2. Oh, this one is 2. Okay.
4 1 3. Yeah.
I think that's correct.
Yeah, before 1, 3, yeah, this is 1, 1 is there, not 2.
Yes, sir, it is correct.
Yeah, because we are coming like this.
Okay.
Okay. So starting from the run of 1, so now in the row-wise scan, so because it starts with 0, so the first number of ones will be 0. Then that will be 6. So that means 0 number of 1, then 6 number of 0, then six number of 1, then 0 number of 0, then 6 number of 1, then 0 number of 0, 5 number of 1, 1 number of 0, then
0 number of 1.
1 number of 0, and this is again 0, 1.
First we gave the number of 1, so
Oh
0
yeah,
number of 1 and 1
0
number of 0.
and then 1, and then 0. Oh no, this 0 is not there. Three, then that is okay. 2, we have 0 and 6. So 1, 0, 1, 0, 1. I think it is all right. So these are the
Yes,
runs. So now this can be transmitted. Now, as you can see, this again can be coded. So this can be coded again. Okay. So therefore, and there has to be a end of line. So one end of line character will be here. So that way one scan can be computed. It's like transmitted row-wise scan, etc. So this is like the essence of run length coding. So the advantage is that we don't have to compute any probability. So thereby, like Hoffman coding, we have to order the probability table, and for a large number of symbol streams, ordering probability table again and again require quite a bit of computational task. So those are avoided. However, here the full object need to be continuously scanned to get these runs. And once runs are obtained, then they can be stacked. As we can see that zigzag scan is more efficient than the
sir.
row-wise or column-wise scan. Yeah. Yes.
So, sir, the zigzag scan will only stop when a different bit is encountered, whereas the row scan will stop even at the end of a row. Is that correct?
Yes. So
Okay.
there are certain advantage, disadvantage from management point of view, data management. So because usually images are not small, so they are very large. So therefore, I mean, often those zigzags can may give, apparently better efficiency. What will happen that this number is growing. Okay. So therefore, we have to put a good amount of bit budget to transmit this number. So that's why if row-wise scan even for a row-wise scan also for a large image, so binary maps, so this number will grow quite a good amount. So therefore, that need to be coded again to make it efficient. Otherwise, these are a string of large numbers. And often it happens that there are many kind of patterns that happen in the binary map. So these numbers can have repetitions. And especially for a row-wise or column-wise scan for a large image, there are so many rows, so these numbers will definitely repeat. And so therefore that we can use like probabilistic coding also by counting this by counting the statistics of these numbers. That is computing the probability of occurrence, and we can use either a Huffman table or some other probabilistic technique to code further to transmit these numbers. So what I mean to say, because here 6 is occurring 4, so probably 6 can be made as 1, 1 can be made as 6, something like, so that we will have 0 can be 5, or 0 is occurring, I think, maximum numbers. So that need to be transmitted accordingly. So we will not go into further detail of such coding schemes. We will go to our just last one we will discuss today, that is LZW. LZW coding scheme is basically Lempel Zip, I mean name of the 3-person. Lempel Zip and Welch. So this was most probably, it was 1970s, as I remember, or you can Google it out when LZW coding scheme was introduced. So here also no a priori knowledge of probability required.
So, like, is this in the Haken book? So,
It is not in the book. So this I will give some material, or maybe whatever we are discussing you can note is sufficient. We will not going into detail of these things. Okay, I mean source coding 2 schemes we have gone little bit in detail. Those only one scheme we have gone through little bit of detail, that is Huffman coding, and little bit of arithmetic coding. And in the book, the next topic is channel coding, that we shall discuss in detail. So this is used mainly again in images. You can get it in any image processing book, like say Introduction to Digital Image Processing by Gonzalez and Woods. These are also given, I mean, they are only small, some introduction is given. There are books on source coding, I mean source coding, decoding techniques. So there the details will be available. So now this is like for for representing like in TIFF format or PNG. they are not that much efficient in coding like JPEG, which we are not discussing because that will take a lot of time. So here, suppose we have a small 4x4 image. Having its pixel values like this.
So this is a 8-bit number, right? So that grayscale value.
Yes, these are the gray values. Okay, so now the idea of this LZW coding is that is to store the chain of occurrences of symbols or gray levels here. Like it can be equally applicable to symbols, chain of occurrences of symbols in a dictionary. So like for this symbol, the valid symbol set is suppose it is an 8-bit. For example, for an 8-bit gray levels, the intensities are mapped onto 0 to 255. The dictionary starts from the location of 256. So that means in that code book, actually there would be gray level entries 1 to 255, and then from 256 the dictionary of chains will be started. So 1 to 255 for gray level, or 0 to 255 for gray levels, and then we have our location 1 to 256. Okay, so this will be location 1 to 256. Or 0 to 255, whatever way we say. 0th location to 255th location. So the image will be scanned, the data will be scanned. 2D data can be scanned. Left to right and top to bottom. So if we scan it left to right, we will find these gray levels of the symbols one by one, and correspondingly we will have the encoded output. So the pixel processed, first we had 39. So 39, and encoded output is of course 39 because no chain is yet formed. So next would be 39. Now here also we have 39, but here one chain will be formed. So we have a location 256, and then we will have entry 39, 39. So basically 256 represent a sequence 39, 39. So 126, no 126 is present. So 126 will be the encoded output, but we can form a chain, new chain here with 39, 126 and code it with 257. Then we have 126, 126. So we can code 259, 126, 39.
So could you explain what is happening here, sir?
Yes. So basically we are scanning pixel wise from left to right. Left to right, 39, 39, 126, 126. Now the coding efficiency comes from the fact that in case of images or many kind of data, we find that there would be some zones having almost uniform or same kind of values, and then it changes to a different value gradually. And so therefore there is a sequence, and that sequence can be coded. So by another one. So like here, once we find that we have two entry, that is scanned 39, 39. So this sequence 39, 39 can be coded with a 256. Assuming that there can be many such 13, the efficiency comes from the fact that instead of representing 39 by 39 and 39 separately as two symbols, we will have one symbol 256, okay, representing a chain of symbols 39, 39. So this is a chain of symbols.
So why didn't you use the 258 location?
258 location actually. Oh, 258. Okay, 258 is here. Sorry.
And sir, why is chain 12639?
Just 1 minute. Let me correct it. 258 is 126, 126. And
Yes, sir.
259 is 126, 39. Okay.
So what was
like that. Okay.
like? How did we make 257? What is like? So how are we deciding what is the encoded output?
Oh, no, so that is sequentially, when we are having a new chain, we are defining a new chain. First, we are defining a chain of two symbols. Okay, initially. As the chain will grow, we can increase the chain length. So like we can make a chain of three symbols. Like say, let us make 39, what was it, 126, 39.
What the dictionary entry? How is it 39 126? Like how are we deciding what is the dictionary entry? So,
No, once, because these are the, we are scanning these values, symbols. So we have 139, then we have next another 39. And then because they are occurring, so this sequence 39, 39, okay. So this we are storing, hoping that this can, if this sequence occurs again, we will have a code word instead of this. If there is a single occurrence, then basically we don't have any efficiency. So therefore, for the next occurrence only, we replace it by a code word. Okay. So encoded output, initially we have 39, 39, 126, 126. The next encoded output is 256. Okay. So that is 39, 39. So corresponding to that, we will have instead of 39, 39, we are writing 256. Okay. So next we will scan 126.
I could understand this table. So how I'm making this table?
Yeah. So 126 and 126 we will replace with 258 like that. So basically the first four values we have encoded output has been given as it is. So that means the values, the symbols we are, while we are giving the encoded output, the symbols itself, we are forming the dictionary. Okay. Now, if there is a repetition of any symbol, we are storing, because we our dictionary location is from 256. So there basically this chain of symbols will be stored by a code word. So that means any chain of two symbols like 39, 39 in this particular case is stored with 256. Similarly, 39 followed by 126 is stored with a code word of 257. 126, 126, it's code word of 258. So therefore, basically, instead of two symbols, suppose here two symbols means 16-bit. Okay. So here, uh, ultimately this dictionary location, whatever values we are storing, that output will give corresponding to two symbols. And this will grow further, like say 39.
Excuse me, sir.
Yes.
Then why isn't this second last 126 coded with 257?
No, no, it is not.
Because upper two are already coded, so it will
It
not
is
pair with that.
256 is already coded. Now we have 257, 258 actually. We have made 258. So that means 126, 126 together we have coded 258. 39, 39 we have coded 256. Okay. Now suppose we have 39, 126, 39, 39. 126. We can have a code word like 260, 39, 39, 126. So we can have coded.
Sir, where is this code word being used? 12639.
No, this is the actual value. I mean, which is occurring 39, then 39, and then 126. This is here. Okay, 39, 39, and 126. So first four values are here, then 39, 39, then 126, 126. Then we take three values together. Okay. So basically this chains of symbols are growing. So now we have 39, 39, 126.
Sir,
Yes.
at 260 location, it will be 126, 39, 39 or 39, 39, 126.
No, 261 would be
Next, sir,
126,
264.
126, 39. Okay. And 262 would be, say, four symbols, 39, 39.
Sir, but earlier you were putting the recent one later in the chain. The more
Yeah.
recent one you were putting at the last, and the earlier one you were putting
No,
at the
because
first.
after these two symbols, actually now we are growing to three symbols. So that's why this is 126 and then 126, 126, 39. Because again, a different we are going to four symbols. Okay.
So,
So
but shouldn't it be in reverse? 39, 126, 126. Because 39 came first, then 126, and then 126.
no, actually we are here, I think 39, 39, 126, and then 126, 39, 39. No, first one is this 39, 39, 126, 126. Then we have 39, 39, 126, 126. Then we have 39, 39, 126. Then we have 126, 39, 39. Okay. So that way it is coming. And next we will have like 39, 39, 126, like four symbols together. So this is the way that concept, you can manipulate it as we scan the symbols. I mean, the concept is like this. So we are basically storing a chain of symbols by one symbol. So this is a very interesting idea that these three people have given, and initially it was very popular, but then when the image size became very large, etc., so then two-stage compression becomes popular. Like instead of one stage of data compression, usually there would be a lossy stage, and then there would be a lossless stage. So two-stage is generally preferable for large data size. So two-stage means first there will be some kind of model, predictive model, but all models are only approximate models. No, these are all lossless. These are all lossless. So all the information in the data is being coded. But in the two-stage, first we have a lossy coding scheme, and then in the coding, in the coder itself, you have to write the decoder. So first do the lossy coding, and then decode that lossy codes, and then subtract it from the original, get the residue, and code the residue in a lossless manner, so that the full information will remain intact. And also, depending on that whether you want that lossy residue or not, we can have the data to be approximated. So that becomes popular when that image size becomes large, and JPEG 2000, etc. standards becomes popular instead of this kind of schemes. So however, all these kind of schemes can come as a, all lossless coding schemes are important because invariably they have to be used to transmit the same model coefficients which need to be transmitted to the other end, and also the residue, because unless the residue is also transmitted, you cannot reconstruct back the original data. So therefore, so for large data, we next day we shall start channel coding. So with this we will conclude here. Often two-stage, sorry. Source coding is used. First one is first stage is a lossy stage. And the second stage is a lossless one. So basically, if we have our data, data is fed to a model. So then model predicts. So prediction. Then we subtract from the original data residue. So both residue and the prediction coefficients of model, that is, those are transmitted. So these two are transmitted. So again, of course, these can be quoted further, the residue and the coefficients of model. So at the receiving end, we have both the residue or the error and the prediction values, so we can reconstruct like the data. So this gives much more efficient coding schemes with this two-stage model. So with that, we conclude our discussion on source coding. There are numerous coding schemes available for various kind of data. So once our source coding is over, then we will be dealing with transform